Language is a tool for composing and combining thoughts. What if we could reverse engineer that tool? Here's a picture of me back when I was young and had a full head of hair. Here are the language centers. Here is where I make the best words. Think of all the genetic and developmental conditions which might affect a person's language skills. It's kind of a miracle that it ever goes right. Some issues can stick with you your whole life, while others can be surpassed. In elementary school, I had a lisp. I got over it with the assistance of a speech pathologist named Suzanne Spurgell. I had to say her name again and again. Thanks, Suzanne. My mother was a language teacher, and my father a neurologist. I've spent my whole life thinking about language and the brain. I always wondered how it started. The most natural way to connect ideas is to speak their words, one right after the other. Think blue sky or go home. Consider the sentence, Jack and Jill went up the hill. Your brain takes that sequence of words and breaks it down into segments. Jack and Jill becomes one segment, up the hill another. It's easy to unpack because everything is right next to the thing it interacts with. But what happens when this becomes impossible? Take the sentence, Jack gave Jill a book. On its surface, it seems to be a sequence of words. The verb gave is directly connected to only two words, the one before it and the one after. This is because we are all subject to the same basic restriction. Words can only come out of your mouth one at a time, single file. Your brain unpacks this sequence into a semantic tree in which the word gave connects directly to three other words, Jack the giver, Jill the recipient, and book the gift. And each link has a different flavor. The mathematics of shape is called topology. Topology will be our central theme today. The process above, also known as parsing, can be ambiguous. Groucho Marx, for instance, made a whole career on this ambiguity. In human languages, we have verbs that can connect directly to three things, like the example above, or two things, or one thing. But there is no verb that connects to four things. Consider what evolutionary processes might have brought all this about. Oh, the dangers faced by early hominids. Note that the word Calvin is next to the word behind, but it's actually the tiger who's behind something. Those who could weave this braid and unweave it into a tree, like the one at the right, they survived the tigers. You are from them. The core human drive is to cooperate, and language is the most potent form of this cooperation. You know, we often look to other wild creatures in nature for biomimicry. We need more biomimicry of humans if we're ever going to achieve artificial intelligence. Look at how much we've already accomplished. The next barrier we must break through is the language barrier. We cannot go around it, we cannot go over it. Too much human knowledge is encoded in language. Fred Jelinek is famous for saying, "Every time I fire a linguist, our accuracy goes up." Yes, when he was working on things, it was much harder to reverse engineer human language, but now that is precisely what we intend to do. My career in computational linguistics began in the mid-90s. I saw speech recognition go from an academic novelty to a ubiquitous feature native to every phone. I witnessed the breakthrough from statistical methods to the neural methods you see referenced above. So many impressive technologies have come and gone, but we are still focused on the computers and not the people. Development is driven by the constraints of computer hardware rather than the shape of human thought. It's high time we rehired those linguists Jelinek fired. We've already realized most of the gains of the neural breakthrough. Accuracy on the y-axis and training set size on the x-axis, it's a classic case of diminishing returns. Similar trends extend across the entire industry. Natural language understanding, or NLU technology and translation, have yet to reach a tipping point like the one we all witnessed for speech recognition. Once accuracy went above 96%, we crossed a tipping point between annoying and useful. NLU and translation are still very far from that tipping point, and it's getting more expensive to boot. By the way, this graph is logarithmic. For the next breakthrough, we must go deeper. We must examine the foundations of language. One morning, I shot an elephant in my pajamas. How he got into my pajamas, I don't know. In the film Animal Crackers, Groucho Marx played with words. He exploited the cracks in the foundation of human language. What is the state of the art? Below the words, you see a gross simplification of a sequence model. Typically, a recurrent neural network is used to process each word in order, and the output is a long vector. Then it does the same in the reverse direction. Their combined states and outputs are used for downstream processing. This can work quite well if two interacting words are right next to each other. The farther apart they get, the harder it is for a sequence model to connect the dots, because as it proceeds through a sentence, each word adds noise to the signal. After all, pajamas is much closer to elephant than it is to eye. This sensitivity to word distance is a weakness of sequence models. Above the words, you see a gross simplification of a transformer model. Every word is connected directly to every other word. It solves one of the weaknesses of a sequence model, but it adds a plethora of others. Neither of these match the shape of how the brain models language. It's all about the topology. Language is tree-shaped. Our central thesis is this: tree models are better for modeling human language because they have the same topology. This is how your brain thinks about language, even if you aren't conscious of it. The left tree represents the idea that I'm the one wearing my pajamas. The right tree is the elephant. There are other ways to understand this sentence, but these are the two salient understandings and the source of the humorous double entendre. Topology determines inductive bias. Each layer of a neural net wants to learn a homeomorphism. A homeomorphism smoothly contorts all the points in a space and respects the rules of topology. Of course, the way a single layer learns says little about the overall function composed of numerous nonlinear stages, but a point remains. If you design a network which is primed to learn a certain kind of structure, and you expose it to data with an underlying structure that matches, the network will easily and happily learn it. Why make things hard for yourself? Why not choose an inductive bias that matches the structure of human language? Chris Manning is one of a small number of top researchers who have worked with tree models. He said that they provide the correct inductive bias for human language and that they really do win. But he doesn't use them now because language is ambiguous and tree models are not GPU friendly. We have a system that uses ambiguity as a feature, not a bug, and it does train efficiently on a GPU. The best test of NLU accuracy would be translation across numerous dissimilar languages. However, the parsers we need do not yet exist. The required effort and expense is significant, so we had to find another way to test our thesis. We used another type of language which is just as complex. Classes of languages are defined by the complexity of their grammars. The lines between these classes are not blurry. This is not a matter of opinion or degree, but rather a clear mathematical concept. Human language exists in a class labeled context-sensitive languages. Apart from human languages, there are an infinite number of context-sensitive languages we could study. Now we need to choose one. One of the most widely studied of these is the language A to the n, B to the n, C to the n. Here we will call it L. This is not a human language, but rather a mathematical abstraction. Each string in L is made up of 3 substrings. Each substring consists of a sequence of the same letter repeated n times. N can be any number, but all 3 parts must be equal in length. Strings that fit the definition of L are on the left. In the first one, there are 2 A's, 2 1's, 2 Z's. On the right, we have rejected strings. For the first one, we see 2 A's, 3 1's, 2 Z's. 2 does not equal 3, so the string is rejected. A well-studied problem in computer science is the task to classify a string as being in L or not in L. This is called the language acceptance task. I trained a tree model to perform the language acceptance task for L. Then I trained a sequence model. Then I trained a transformer. Each training run was limited to 300 seconds on a MacBook Pro. The tree model worked well from the beginning, but there were problems with the other 2. They performed so poorly they could not even compete. Eventually, I discovered a way to give a leg up to the sequence model. I devised a tuned curriculum learning regime which helped it achieve the results you see in red above. Even so, it's still far behind the tree model. And I never found a way to help the transformer model. In the time allotted, that never went above 55% accuracy, so I left it out of the graph. Note something about that red line. Sequence models perform worse on the largest sets of training data. those with more than 2 to the 15 samples. This is connected to the time constraint. Whereas tree models can learn equally from any training sample, the sequence model suffers from a peculiar difficulty. It does not learn the same thing from each sample. Even if it eventually gets to the same end state, this observed training path dependence of sequence models hints at a larger inability to generalize context-sensitive structures. Although I first thought of this idea back in 2010, it took until 2015 before the provisional patent was ready. The full utility patent was accepted in 2018. It covers a set of ideas that could be central to the future of NLU. Before we end, let's apply to some existing work. Consider the knowledge graphs used by James Pustojovsky in his generative lexicon. These graphs can be learned automatically from existing techniques. Focus on the first one, the type graph. Remember this tree? Let's use a type graph to generalize it. We turn elephant into animal, pajamas into clothing. Pull out that subtree, animal in clothing. If a computer read a billion words of English prose, how often might it find the subtree, animal in clothing? Remember the other tree? In this understanding, the narrator is the one in the pajamas. This time we get the subtree, I in clothing. If a computer read a billion words of English, how often would the narrator be in clothing? I posit that humans will be in clothing more often than animals. These frequencies can be used to resolve conundrums without human intervention. Human language, and perhaps even human thought, is shaped like trees. My name is Graham Moorhead. If these concepts resonate with you, reach out. I want your advice and I need your help. Together, we can leapfrog the current state of the art.